Hello, everybody. So this is going to be our last section in Chapter 7, the sampling distribution of the sample proportion. And now we're not looking at the sample mean, we were looking at proportions. So let me show you what a proportion actually is first. So let's say we just had like a pie graph, and we were looking at this part right here, which I'm just going to make it 70%. That means this part over here is going to be 30%. Proportions are going to be a representative sample or representative proportion, I guess, of a population. All right. And normally when you have these, some things have already happened. For example, this is red p hat. Put a little hyphen there so it doesn't look like fat. So p hat, and this is our sample proportion. Now, p hat is going to be equal to x over n, where x is going to be the number of successes divided by the total sample space. So it's almost, if you think about it, it's just like trying to find a probability. It's the number of successes divided by the total sample space. All right? Now, we can use p hat to approximate the population proportion. Okay, and that, you got to remember, is a parameter. Okay? So, one thing I just want to reiterate, because we are doing inferential statistics, okay? In chapters 8 until the end of the semester, here's what we're going to be doing. We're going to be looking at data that is collected from a population. In other words, we're going to be looking at sample data, and we're going to use that data to try to make a generalization about a population. Because once again, there are restrictions that prevent us from testing every single person within a population. Sometimes you can do it, a lot of times you can't. All right? So our goal is to take these sample statistics, in this case it's going to be p hat, and use that to approximate the population proportion itself. All right? Now, there is a relationship between Chapter 5, Section 2, which is the binomial probability distribution, and a normal distribution. In fact, we already seen it. If you think about it, if we go back to the candy example, where is my candy example here? There we go. Here is my candy example. If I uncheck the normal approximation, just put in exact, all right? We know with a binomial probability distribution, the number of successes is given to us. So in this case, let's assume it's 5, or it's 0.5, I'm sorry. And the number of candies that we're going to draw each time is going to be 10. And I'm just going to take one sample out. So when I draw out 10 candies, notice I get a mean of 6.0. And remember how to calculate mean. All right? Mean, let me go back to our notes for a binomial probability distribution. So for a binomial probability distribution, mu is equal to n times p. The variance is equal to n times p times q. And the deviation the population deviation is equal to the square root of n times p times q, okay? So when we go back to the candy distribution, we can see only one sample, and here's my little dot right there. All right, that's the first sample. The green bars represent what a binomial probability distribution looks like, okay? And if I keep just taking samples, let me get rid of this animation here. I don't want to see it every time. If I just keep taking samples here, let's go to 30. All right, notice it's kind of looking normal. It's not perfect. It's far from perfect. But if I increase the number of samples, oh boy, what did I just hit? Oh, there we go. Nice. So if I increase the number of samples, every time I click draw samples, it does 10 at a time instead of only 1. And I just let this start going, you can start to see how quickly this starts to turn into a normal distribution. All right? So we can use that to our advantage here. Okay, so here's our big definition of this section. Properties of the sampling distribution of the sample proportion. This is different from the previous section. Previous section was the sample mean. Now we're talking about proportions. So if a random sample of n observations is selected from a binomial population with parameter p, then the sampling distribution of the sample proportion, p hat, is going to be defined as x divided by n. We'll have a mean of p and a standard deviation equal to the standard error of p hat is going to equal the square root of p times q all over n. And notice, all of that is underneath the radical symbol. Q is defined as 1 minus p. And note, forgot a letter E here. And note, when the sample size is large, the sampling distribution of p hat can be approximated by a normal distribution. So the approximation will work, so it's going to be adequate if, and you got to meet these two conditions, n times p is greater than 5, and n times q is also greater than 5. So if you meet those two conditions, we can use everything that we just said up top. So let me go ahead and let me show you an example of where this actually occurs. All right, so here we go. Sorry, I'm feeling a little bit lazy, so I'm just going to copy and paste this from our textbook into our notes. So I'll read it for you. From driverless cars to a workplace staffed by robots, automation has the potential to reshape many facets of American life. The large majority of Americans, 87%, would favor a requirement that all driverless vehicles have a human in the driver's seat who can take control of the vehicle in the event of an emergency, while 56% of U.S. adults say that they would not ride in a driverless car. So that little asterisk, if you went to our online text, you can click that, and that would give you the report on which they actually got these numbers from. If these figures are correct, what is the probability that in a sample of n equals 100 U.S. adults, the sample proportion, p hat, of adults who would not ride in a driverless vehicle falls between 55 and 65% respectively? So before we do anything with this problem, all right, we need to establish some stuff. First, we got to let x equal something. So in this case, since they're asking us about the adults who would not ride, we're going to let x be, or let x equal the number of adults who would not ride in a driverless vehicle. And I don't know, ask yourself, would you ride in a vehicle where there's no driver? It's just driverless? Oh, can't even spell vehicle correctly. I think I would. Now, we need to check their criteria because they're asking us to use the sample proportion and find the probability that in a sample of n equals 100 adults, that this sample proportion who would not ride falls in between 55 and 65% respectively. So what we need to do is we need to check the requirements first. So remember, n equals 100, and the requirements are n times p has to be greater than 5, and n times q has to be greater than 5. So p is going to be the probability of success. So what we found was, and this comes directly from the numbers, 56% of U.S. adults say they would not ride in a driverless vehicle. That is the probability of success. Now, in this case, success means you're not going to ride. Don't automatically assume success is always like a good thing, all right? This isn't a bad thing either. It's just we're defining success as somebody who will not ride in a driverless vehicle without a driver, okay? So P is going to be equal to 0.56, which means Q has to equal 1 minus 0.56. And if you take 1 minus 0.56, you're going to get Q equal to 0.44. So we have 100 times 0.56, and that is absolutely greater than 5. In fact, it turns out to be 56, which is bigger than 5. Check. And then 100 times Q is going to be 100 times 0.44, which is obviously greater than 5 because 100 times 0.44 is going to be 44. So definitely bigger than 5 for each of them. So the normal approximation is going to be appropriate here. So we can go ahead and say, well, we want to find the probability that the sample proportion, p hat, is going to be in between these two values right here. 0.55, which is 55%, and 0.65, which is 65%, respectively. So what we're going to, I don't know why that happened. So what we're going to have to do here is we're going to have to find a z-score for 0.55, and we're going to have to find a z-score for 0.65. Now, we know the standard error is a little bit different. So z, in this case, is going to be p minus, it's going to be p hat minus p, all divided by the square root of pq over n. Okay? So let's go ahead and let's do the first one. We'll do z of 0.55. So that's going to be 0.55 minus 0.56, all divided by the square root of 0.56 times 0.44 all over 100. Now, before I move any further, I want to make sure that we all understand where these numbers are coming from. So let me just scroll up here a little bit. Remember, P and Q are parameters. They come from that massive survey that, and I'm going to scroll up a little bit more. Those numbers came from this survey that we found. 56%, you know what? Too many underlines. Too many underlines, let's highlight. We'll use a different color. So that comes from this data that's been collected here, okay? P hat represents these values right here, 55% and 65%. Okay, so there's a difference there, right? You got to be careful. The hardest part about this is just knowing what numbers go where and what they represent. P hat is a sample proportion. P is a population parameter, okay? It's going to be the population proportion here, all right? So make sure that you're aware of this when you're making your substitutions, all right? I know they all look very similar, but if I were you, I would maybe do like flashcards and write down statistics and then write down all the statistics like X bar, P hat, the letter S, and then the other one, make it population parameters and make that mu, sigma, and P, okay? All right, so back to this. All we have to do now is just crunch the numbers. Now, you got to be careful with all of this stuff in the bottom, all right? If you need to, do it one step at a time. Take 0.56 times 0.44, divide it by 100, and then take the square root, okay? It's very important that you do that, all right? But if you've done this correctly and you've crunched the numbers correctly, you should get negative 0.20. So let's just go ahead. Let's make sure that I'm correct. So I'm going to do this again. So get out my calculator here. All right, so there we go. And I'm going to just go ahead and just start typing in the numbers. Like I said, I'm going to keep it nice and simple. So in the numerator, 0.55 minus 0.56. All right, well, that's going to be negative 0.01. So I'm going to go back to our notes. Write that down, negative 0.01 over. And now I'm going to be focused on that denominator, and I'm going to do it one step at a time. 0.56 times 0.44. All right, that gives me 0.2464, but then I'm going to divide that by 100. All right, that gives me 0.002464. And then I'm just going to take the square root of that number. And that's going to give me 0.049, a bunch of numbers. So give me a sec. 0.04963. So I'm going to write that down. 0.04963. Notice I kept a bunch of decimal places. And when I divide these two numbers, negative 0.01 divided by that enormously large number. Oh, I didn't hit the right thing. So let's quit and clear. Let's do it again. Negative 0.01. There's my division sign. I'm going to divide it by 0.04963 in all those decimal places. And I come up with negative 0.201, which I just rounded to negative 0.20. Now, if you're asking yourself, well, why did you only round it to two decimal places? We are finding a z-score. And we know if we use the table, z-scores are only good to the 100th position. So there's my first z-score. Now we're going to do the same thing for 0.65. So we get 0.65 minus 0.56, all divided by my standard error, which is going to be 0.56 times 0.44, all divided by 100 underneath the radical. And if you do this correctly, you're going to get 1.81 for a z-score. So on your table, or better yet, on your graph, we know P is going to be right down the middle. All right. Now what we're concerned with is, excuse me, the value of P is 0.56. So where does 0.55 fall? Well, that's going to be to the left. And 0.65 is going to be on the right. So we're concerned with finding that in the middle. So what we can do is we can look up these two z-scores, negative 0.20 and 1.81. So I'm going to go ahead and do that for us. Oops, sorry. Let's go back to chapter 6 because I just want to show you how to use the table again. So here's our table. First one is going to be negative 0.20. So z equals negative 0.20. So negative 0.20 is going to be right here. So here's my negative 0.2. And then the first column here, if it'll let me scroll. I hate when it does this. My first column is going to be 0.00. So I just come all the way down and to the right. And I found that that area is going to be 0.4207. So the probability that we're in between these two z-scores right here, which is equal to the probability that P hat is in between 0.55 and 0.65, is going to equal 0.4207. And now we need to find the z-score for 0.65 and the area for that. So we go back here to our table. This is going to be z equals 0.65. All right, so let's see. So here's 0.6, and there's the 0.5. So I come down and I look, and that's going to be, oh, sorry, wrong number. Jeez, I was thinking of the proportion. We need 1.81. Woo, I'm glad I caught that. 1.8 is right here. There's my 0.1. Sorry about that. So there's our value right there. It's going to be 0.9649. So let's go back to our notes. I'm going to put that all the way up top. So 0.9649. And when you subtract these two numbers, you get 0.5442. Okay? Now, if we want to interpret this, think about what the question is asking us. The question was asking us, if these figures are correct, what is the probability that in a sample of 100 U.S. adults, the proportion is going to be in between 0.55 or 55% and 65%? So what I can say is the probability of selecting (100 adults) and determining that the proportion of adults that will not ride in a driverless car falls in between 0.55 and 0.65 is 0.54, or if you want to convert these into percentages, 55 and 65% is 54%. In other words, if you were to randomly select 100 adults, you got a 54% probability that the proportion of those 100 adults that you sampled will be in between 55% and 65%. Okay? So you got to be careful with which one of these you use, because we looked at two different sampling proportions or sampling distributions. In section 3, let me go all the way back up. In sample 3, we were talking about the central limit theorem and the sample mean. In section 5, we're talking about sample proportions, and that's the difference. Okay? So I hope this helped, and good luck this week. I'll see you in chapter 8. Bye.